Hadrons are subdivided into two categories. Hadrons can either be baryons or mesons. Baryons are kind of like particles. I think of them as a particle like the proton and the neutron. They build stuff. Baryons have spin 1/2 or spin 3/2. They have what we call a half integer of the spin. That might seem like a funny coincidence, but it turns out there are some deep theoretical reasons why this is the case. But in the 1950s, it was just an observation. These things, like protons and neutrons and delta particles, the one that looks like heavily protons and neutrons and decay into protons and neutrons, they all have spin 1/2 or spin 3/2 or maybe even 5/2, but never anything that's not an odd number divided by 2. So that's just a sort of a weird fact at the time, which we will come back to later. The mesons were first invented by the theorist Mr. Yukawa in the 1930s. He proposed the existence of the meson as a way to explain forces. They were like forces. They are like the force carrier for the strong force. Well, at first we only had the pion, and then there came all these heavy versions of the pions, the kaons and the low particles. And a whole bunch of them that were like heavy version that could decay into other mesons or other particles. All of these mesons had either spin 0, like the pion. Some of them had a spin 1 or spin 2. They were always integers, pure integers. All mesons seems to have an integers amount of the spin. So there was some order in this chaos. There were certain patterns beginning to appear, and in the 1950s, it was still a little bit overwhelming, but people were hunting. They were trying to find some organizing schemes, anything so that we didn't just have to have a random collection of the data in a table that was the only way of understanding the world. That would really have been shame. When you are organizing particles, each particle can still have quantum numbers. So, for example, you have various kinds of the mesons. Some of them might have a strangeness 0, some of them might have a strangeness +1, and some of them might have a strange -1, strangeness -1. They are still all potentially mesons if they have an integer spin. If they can be produced in any numbers, there are various characteristics that define what is meson or baryons. So you can talk about the strange mesons or non-strange mesons, and the strange baryons or the non-strange baryons. So we are beginning to categorize in this way. There is another way of categorizing that people think about based on this idea of the spin. At first, it wasn't clear exactly why spin was so important. I'm never really going to be able to explain to you deeply, mathematically why spin is so important, because it's a pretty formal mathematics that connects spin to the properties of the particles. But it was observed that every particle in nature, every particle either had a half integer spin, 1/2, 3/2, 5/2, or integer spin of 0, 1, 2, or 3. That's a different way of categorizing particles. If you have a spin 1/2, then you are called a fermion, named after Mr. Fermi, Enrico Fermi, in honor of the Mr. Fermi. Any particle of nature that has a spin 1/2 or 3/2 is called a fermion, whether you interact strongly or weakly. An electron or proton, they are all fermions. They are all fermions. I generally think of the fermions as the particles. Electrons, muons, protons, neutrons all have spin 1/2, and I think of them as the little fundamental particles. If you are not a fermion, you are a boson. I love that word. it's a little bit of silly name, although it's named in honor of the great physicist whose name is hard to pronounce, Satyendranath Bose. He was an Indian physicist in the early part of the century. It was in the 1920s, I believe, when Bose did his theoretical work. He argued mathematically that a particle with a spin 0 or 1 or 2 integer spin should behave very, very differently than the particle with a spin 1/2. He said that if you have two particles of integer spin, even identical particles, that they can sit right on top of each other and they are not only perfectly happy, they actually like it. It's more probable for bosons and any particle with integer spin to sit on top of the identical bosons. That's crazy idea. We are talking particles here. How can two particles sit on top of each other? Well, bosons are unusual particles. The most famous example, my favorite example of the boson, is a photon, the particle of the light. And yes, it is a particle, but it's also a wave. I think it's not so hard to visualize light sitting on top of the other light. It's just a brighter light. In fact, that's exactly what a laser beam is. A bunch of photons, which are identical, which sit right on top of each other in space and in time. Wow! So, you can pile on more and more and more. Piling up, right? So cool. The more intense your laser beam is, the more bosons you have put together. So photons, it turns out, have spin 1. Photons do carry angular momentum, and because it's an integer, they can sit on top of each other. This is what Mr. Bose discovered, and hence the name bosons. The name was given to these particles by Mr. Dirac, who was also thinking about the theory of bosons and fermions in later years. Fermions, spin 1/2, are the exact opposite. They are the antisocial ones. They don't like to sit on top of each other. In fact, if they are truly identical, you cannot make them sit in the same place at the same time. That's Mr. Pauli's exclusion principle, and it's a very deep mathematical property of quantum mechanics. So, I think that's why I think of a spin 1/2 or fermion as a particle Y, particle E, because they don't want to sit on top of each other. That's why that's my image of particles. That they can be on top of each other. Bosons are more like photons, so I think of them more as a force carriers. Except you know it is a pion and it's exotic heavy partners. Is it a particle or is it a wave? Well, it's a base boson. It's a boson. It doesn't make sense to ask It doesn't make sense to ask is it a particle or is it a wave in the quantum mechanics. Everything is both. Stuff, it hurts your brain a little bit, but it's hard to visualize that at least there is some mathematical order and organization scheme to all of this stuff. Wow. So what about simplicity? Alright, we began arguing that the goal in the 1950s was to make some sense of this pattern of the particles. At first was not even a pattern, there were just masses and charges. It's just numbers. It's like collecting data. We were beginning to see some organizational schemes. We were kind of the physicists of the 1950s, acting a little bit like Johannes Kepler, who figured out from the data that particles move in elliptical orbits. We were learning that the particle had new quantum numbers such as strangeness. They could be bosons or fermions. There were categorizations. In fact, there were some deeper patterns that people were beginning to observe, and these deeper patterns were really hints that there was some part of the story that was still missing. For example, you had the proton and the neutron, these two particles which are in almost every respect identical. Okay, they do have different electric charge, so they are electrically different, but as far as these strong interactions are concerned, a proton attracts a proton, or a proton attracts a neutron in basically the same way in the strengths of their interactions, right? Their properties and their masses. Everything is almost nearly identical, so we say they are doublet, right? Doublet. Two particles that are intimate partners. You start looking around in nature and you discover there are many such partners. For instance, Mr. Yukawa's pion. Mr. Yukawa predicted 3 pions, a pi plus, positively charged, a pi minus, negatively charged, and a pi zero, electrically neutral. There are 3 particles, a triplet of the particles which are, in almost every respect, identical. They have almost exactly the same mass, the same spin, and the same basic strong interaction properties, but they are distinguishable because of their different charges. This pattern continued. When they looked at the 3 particles with a strangeness, they discovered that, for example, that there was a strange meson called a kaon. It was called the kaon, not a Greek letter, because it was discovered in an American laboratory, and somebody noticed that many times this particle would leave a track in the bubble chamber. Where one particle was coming in, the 3 particles went out, and they looked like the letter K. So right, you get to name the particle if you discover it. So they called it the kaon. People were getting a little bit whimsical, and it will only get worse as time goes on. The kaon is a meson. It's kind of like a heavy version of pion, and this kaon has a strangeness number. Well, it can have various different strangeness numbers. In fact, it turns out that there are 4 different kaons: a positive kaon, a negative kaon, a neutral kaon. Now you are asking, what on earth could be the 4th one be? And the answer is another neutral one. Whoa! So what's the difference between the 2 neutral kaons? One of them has a positive strangeness, one of them has a negative strangeness. Wow! It's a kaon and an anti-kaon. Wow! Okay. If you have a particle and its antiparticle, they have opposite electric charges. They will also have an opposite strangeness number. So in this way, people were discovering a quadruplet of particles that were intimately connected. They were very close in the mass and in the properties. So what was going on? How could they explain these triplets and quadruplets? In fact, people discovered octet of the particles and decuplets. So there is some order coming out. Murray-Gell-Mann came up with a sort of an organization scheme in which at least you can assign numbers and categorize particles as to whether they belong in a doublet or a decuplet. He called his scheme the eightfold way. It's kind of the tongue-in-cheek reference to some old Eastern philosophical writing of the Eightfold Way, and I think that he later came to regret this use of the mystical term for physics because people jumped on it. Okay, right? This was in the late 1950s and the early 60s. I think people began to connect particle physics with the mysticism in the popular literature in a way that I think it pretty much annoyed the particle physicists because they were just collecting data. There is nothing mysterious or magical about what they were collecting. There were tracks in the bubble chamber and they were just organizing them, but it just seemed like a cool name to him at the time. Murray Gell-Mann's Eightfold Way is still not an explanation of anything. It's kind of like Johannes Kepler's observing that certain organization or certain organizing principles such as planets move in the ellipse or that radius of the planet is related to the period. The radius, meaning the distance to the sun, is related to the amount of the time it takes to go around. He was just noticing order in the complexity of the data. Still, nobody has an underlying story and explanation for why are there 4 kaons or why there are all these particles. Ultimately, it was Murray Gell-Mann, actually not alone, who came up with an explanation and an underlying picture. There were lots of ideas. There were people, for example, who argued that it was just nature and nature is complicated. There was a program of theoretical research called the nuclear democracy, where every fundamental particle that we had discovered was equal in every respect. It was a democracy. It meant that no particle was better than any other particle, that all particles could be thought of as a part of this web of fundamental particles. It was a neat idea, right? There is always some connection between the scientific ideas that you have and the politics and world view of the scientists who are trying to be creative, who are trying to understand what's going on. That idea ultimately failed, and Murray Gell-Mann's idea, which was more reductionistic, said that we can explain this complexity in terms of the something underneath, and that ultimately has proven to be much more varied and descriptive way of understanding the zoo. Yeah. Murray Gell-Mann suggested that perhaps all of these particles, the kaons and the pions and the protons, all the strongly interacting particles were built of 3 simple building blocks. He gave them the name quark. It's a whimsical name, and I'm not quite sure why he picked that name. He said that he thought they were kind of quirky. To propose something brand new, something smarter, something smaller than anything that had ever been seen. He was a fairly literate man and was reading James Joyce's Finnegan's Wake. There is a passage in the Finnegan's Wake that says 3 quarks for Master Mark. And there were 3 quarks in his model anyway. That's the term that he picked. By the way, if you're a literature fan, you look at the passage, you might argue that it should be pronounced quark, because it rhymes with a mark, but Murray Gell-Mann invented the particle and he insisted that it's quark. He invented it, so he gets to tell you how to pronounce it, and that's what we call it, right? The quarks then are the ultimate building blocks. In our next lecture, we are going to really talk about the theory of quarks and how we make sense of that zoo by postulating the existence of 3 particles. They are going to be strongly interacting. You are going to put quarks together, and proton, for example, is going to be a combination of some quarks. Just as an atom can be understood as being built of the simpler things, a nucleus and some electrons. So that's a lovely organizing and simplifying principle. In fact, one of these 3 quarks, or rather the sort of exotic one, is going to be called a strange quark. And so what is the strangeness number? It's how many strange quarks are inside of you. So if you have a particle that's observed, it was already tabulated to have strangeness 1. We will understand what that really means is that one of the quarks is an S quark or a strange quark. If you've got a strangeness 2, it means 2 of your quarks are strange quarks. So the strong interaction can create a strange quark and anti-strange quark, and that's how it is that we are going to conserve strangeness numbers. We are going to understand all the phenomenology, all this orderliness that was beginning to develop in the 1950s by proposing this simplifying idea. In order to really understand quarks, the strong force that binds them together, we really have to take a break for a lecture from all these particles and talk about forces. Now I've been talking about forces in the rather casual way so far. I've introduced the idea of the force as being mediated by the particle. You create a particle, you toss it over, and the other particle absorbs it. That's a way of thinking about forces, and it's useful to try to develop that a little bit more formally. In the 1950s, a lot of physicists were working on this idea, and they were in particular trying to understand the simplest force at that time, which was electromagnetism. Electricity and magnetism was sort of the oldest and dearest force to everybody, well understood already in the 1800s. So this theory of fundamental forces developed, and there were a lot of trials and tribulations. We really need to talk about how that all works, and then we'll put everything together, the nature of the forces and the nature of the particles, and talk about the quark model of the strongly interacting particles. Thank you!